This is ISAT 30, Sustainable Manufacturing Systems. Today we're going to cover forecasting. So mainly we're going to discuss what is forecasting in manufacturing systems and also what are the quantitative and also qualitative methods in forecasting. First, what is forecasting? So forecasting mentioned is very important in strategic planning as well as operations planning. We usually categorize decisions into three major aspects: long-term decisions, medium-term decisions, and also short-term decisions. So long-term decisions is more dealing with strategic plannings. And for example, if you want to introduce a new product, probably you're going to need a couple years or even longer time for its introduction and R&D. And well, if the medium-term decisions, we're probably dealing with inventory control as well as different production plannings. While short-term decisions we're mainly dealing with really maybe daily or weekly decisions. For example, scheduling of job orders and also dealing with some of the issues that occur on the shop floor. All right, so there are both qualitative methods as well as quantitative methods. So qualitative methods include market research such as opinion polls and also interviews. We collect those information from customers to get an idea what is the market is thinking about. Well, there's another method. It's called a panel consensus. It's called Delphi method. So Delphi method is a little bit different with panel discussion. So in panel discussions, usually we collect experts' opinions and let them discuss and come up with certain opinions or ideas. Well, in Delphi methods, because in traditional panel discussion, usually the ideas or opinions will be led by only one or two persons in the panel. So in this case, Delphi method actually is trying to avoid this kind of issue by collecting opinions from experts individually. So before they get a chance to discuss anything, we first collect their ideas first. In this case, all these opinions from experts can be collected. So this is Delphi method, and also we can use if we do not have any product in history or do not have much information from the past. Then in this case, we can use some analogy. For example, if we are introducing a new product, but we do not have that kind of product in the past or similar product in the past, then we're probably gonna look at some other companies' products and then see when they are experiencing a similar situation, how their product are behaving in the market. So this is a historical analogy. Well, for quantitative methods, there are time series analysis, causal relationships, and also simulation. So time series analysis mainly is using historical data to find out the predictions or the patterns of from the historical demand or the sales in order to give certain predictions. Well, causal relationships is mainly dealing with look at what are the relationships between different factors and then trying to find out what are the predictions. Well, simulation mainly is looking at the model of the whole market and also their own company's situation in order to generate the simulation model, and then by manipulating some of the factors in the model and then give predictions to the simulation. In this course, mainly we're primarily focusing on time series analysis. All right. First, let's look at in the demand or the forecast. What are the components? This is a graph of the sales over time since 2008 and 2016, and of the Apple's iPhone shipments. You can see it from the lines. There are fluctuations, there are waves, there's a trend. So usually we use average, seasonality, and the trend to look at what are our sales, because Because during a certain period of time, the sales can have a certain trend, either because the company is growing and the market is expanding, but also there's seasonality because at certain times there's introduction of the new products. For example, iPhone release their new phones or their new products every fall. Well, in this case, you can see there's a spike in the fall every fall. So this is seasonality. All right, so usually for the components of demand, there are average, trend, seasonality, cycles, random variation, and autocorrelation. And in this course, we are mainly focusing on average, trend, seasonality, as well as random variation. Okay, so first method we're going to introduce is a simple moving average. So moving average has been used a lot in many different data analysis and predictions. So from a simple average, we can see what is a foreseeable future in the next period, and a simple moving average is to calculate the average demand over the most recent periods. For example, sometimes we can say, oh, it's a 7-day moving average, it's 3 weeks moving average, or 3 months moving average. So this really depends on how many periods you are using to find out the next prediction. All right, so the formula for simple moving average is F equals to AT minus 1 plus AT minus 2 plus until TAT minus N divided by N. So the F is the forecast for the coming period, while N is the number of periods to be averaged. And AT minus 1 to AT minus N, these are the actual demand or actual sales or actual occurrence, the number that has occurred in that period. All right, because in simple moving average, we give equal weights for all the periods, but actually in the real situation, that the closest period probably have a better indication for the next period. So that's why people have invented another method which is called a weighted moving average to give closer periods of the higher weight in the prediction or in the forecast. All right, so the formula for that is Ft equals to W1 times AT minus 1 until Wn times AT minus N. So we know what is AT minus 1 until AT minus N, but the weights are W1 until Wn. And here, W1 plus W2 until Wn equals to 1, right? Because these are the probabilities, and we should put them all into one to make one single case, right? So this is the weighted moving average. Because those equations are pretty straightforward and simple, I'm not going to use any examples to demonstrate that. And well, in order to choose a better weighted better weights, first you probably want to conduct some experiments or trials, and then to find out what are the better weights to assign in this equation. And it's not just based on your own intuition. Well, sometimes you probably can do it, but mostly you have to rely on the historical data from data analysis to find out what is the better weight for that. Well, the weakness of moving average is that you will have to carry a lot of the historical data, and managing of such the data will be some of the effort you have to put in, because moving average can be weeks, days, weeks, months, and even years. Then you'll have to keep all this data in your system. All right, another method is exponential smoothing. So exponential smoothing means we are going to use the closest period of data and predictions in order to find the next period's data and prediction. So and the reason we are using exponential smoothing is that we do not need to keep all those data, historical data from years ago or weeks ago. We just only need the most closest periods data. So that's exponential smoothing. and it's easier to work, and it does not require a lot of storage of the data, and also it limits our computation power in we do not need a lot of computation power in our model. And the formula is FT is the exponential smooth forecast for period t, and FT minus 1 is the exponentially smooth forecast made from the prior period. Remember that F is always the forecast, it's not the actual. But A is the actual demand, right? A is actual demand. So you can see this part, A t minus 1 minus F t minus 1, this is what? This is the actual minus the forecast, which means that's the error, right? So this is the error. This is the error that has happened from the actual demand and the forecast, right? Well, in order to embed this error in our next forecast, then we're going to use a smoothing constant alpha, right? Smoothing constant alpha to trying to embed this error in the next forecast. And remember, this forecast ft minus 1 is a prior forecast, prior period forecast, plus the error or the difference from the actual and the prior forecast. So this is to generate next forecast. You can see, if we have big error, what happens is this part will be bigger, and then will be incorporated into next forecast by adding that kind of error. So this is exponential smoothing. Now let's use one example to look at this. So the example is last month's forecast was 1050 units. If 1000 actually were demanded rather than 1050, the forecast for next month will be, and assume that the smoothing constant is 0.05. Alright, so we know the last month's forecast is 1050. Okay? This is the last month's forecast. And the 1000 is the actual demand. Right? We know now we can find out the difference from 1000 to 1050. So it's the 50 units difference from our forecast and the actual demand. And now we're going to find out what is the next month's forecast. All right, so the equation is FT equals to last month's forecast, right? Plus the difference, this is the smoothing constant. Then we can find out it's actually 1050 plus 0.05 times 1000 minus 1050. Remember, it's the actual minus the forecast. Then we got the number is 47.5 units. All right. Now let's look at another equation, which is exponential smoothing with trend. Because when we are looking at the exponential smoothing, we are only using the what? We are only using the last period's data, but without considering a lot of other factors. But remember, in forecasting, we have average, we have a trend, we have a seasonality, a lot of those. If there is a trend, in our forecasting, so what we're going to do is we'll probably want to incorporate the trend factor in the exponential smoothing. So this exponential smoothing with trend forecasting is about this. All right. So the first part is ft equals fit t minus 1 plus alpha and the difference. And something you will note is that fit is forecast including trend, right? Forecasting including trend, and ft is forecast with odd trend. All right. So fit t minus 1 basically is the forecast from last periods, right? It's the same as exponential smoothing. We are only the only difference that we are using, the trend, adding the trend in it. All right. So the forecast we generate from the first equation is ft. So this ft is without trend because we haven't counted trend factor yet. Okay. Then we need to generate what is the trend, right? What is the trend factor here? So trend tt equals to t minus 1. T minus 1 is the last period's trend we calculated, okay? Plus delta. So delta here is a smoothing constant for the trend itself, for the trend. And how to find out the trend? We use ft, which is, right, this period's forecast minus prior period's forecast with trend. right? We already calculated from the first equation of ft minus fit, which is forecast with trend from last period, and times delta. Then we can get the trend factor. Then the final equation or the final forecast, including trend, will be ft plus tt. So this is how do we find the exponential smoothing with trend. All right, next let's look at one example. So assume a previous forecast including trend is 110 units, a previous trend estimate of 10 units, and an alpha of 0.2 and a delta is 0.3. Now we have the smoothing constant for those. If actual demand turned out to be 115 rather than forecast 110, right? Calculate the forecast for the next period. All right, now we know what? We know that the actual demand, right? We know the actual demand, which is our A, right? And the forecast is 110, right? It's a previous, so it's what? It's a forecast including trend, right? Forecast including trend from the previous period, right? From the period, if it is t, this will be t minus 1, right? 110. And this will be t minus 1. Okay? And delta, we know the delta, we know the alpha. We also have the previous trend estimate, which is t minus 1, and equals to 10. Now basically we have all the variables and the data for that. Now let's calculate. Okay, so ft first equals to fit t minus 1 plus alpha a t minus 1 minus fit t minus 1. So this is the 110, it is the prior forecast, right? Plus 0.2, which is alpha, smoothing constant for alpha is 0.2 times 115, which is actual demand minus 110. All right, so we calculated, first equation calculates the forecast without trend, right? Forecast without trend for the next period. And then next we're going to find out what is the trend for next period. The trend equals to the prior period's trend plus delta. Delta is 0.3 in this case, which is our smoothing constant for trend, times ft, which is a forecast without trend from the first equation, minus fit, which is a prior period's forecast. Then we can calculate the trend factor is 10.3, and the forecast without trend is 111. Now we add them together, will be 121.3. So this is how we find out the next period's equation. All right, so if now it continues this question is if instead of 121.3 the actual demand actually turned out to be 110.20. All right, so the sequence will be repeated and the forecast for the next period. So basically the ft becomes the prior periods. Now we are looking at the next period after the ft, right? So ft will becomes fit becomes fit t minus 1. All right, so basically we're going to use the same formula, and ft plus 1 equals to 121.3 because it's our prior forecast with trend, right? Plus 0.2, which is the alpha and the smoothing constant, right? 0.2. And 120 is used because the actual demand is 120, right? Now we are moving forward, right, to the next period. Minus 121.3. Now we calculate the next period's forecast without trend, right? And the trend factor, consequently, we can calculate what is the trend factor, as in the forecast including trend will be 131 point. Actually, this is FIT t plus 1. Right, it's FIT for it's forecast including trend. Okay. All right. So how to choose alpha and the data? So alpha and the data really depends on how random variations are presenting in your historic data. So usually include some data analysis to find out alpha data. In this course, we just gave you the alpha and data to make problem simpler. And it really depends. Also, it depends on how steady the trend is. So if the trend is really steady, means that alpha probably gonna be a little bit smaller. But if the trend is a lot higher, then probably gonna put the alpha on the data a bit higher. So next is we talk about the trend, but how do we find, if we have a series of data, how do we find a trend line, right? Because if we have many periods, usually we use a trend line to give estimation to find the trend. And for the trend line, we have to use a linear regression model or analysis to do it, right? So, and usually it's because it is for long-term forecasting. And the equation for linear regression is y equals a plus bt. We are all familiar with this equation. And now let's look at one example here. For example, the quarters here, the table to the right, we see there are 12 periods, right? 12 quarters of the sales from 600 to 4,900. And now if you want to map out, the all these points in the graph is in our green graph. You can see so little y1 to little y12 are the actual demand, right? Actual sales that from the table. So little y1 to little y2, little y3, little y4. Well, also we draw basically we want to find a line that is best fits its trend, right? Best fits its trend. We can draw a lot of lines, right? You can do it a little bit longer, higher, or a little lower, but want to find out the one actual line that is the best fits its trend. So which is the red line. Then how do we find out the red lines? So first we can assume there is one red line that best fits its trend, right? We assume that, and for each of the quarter, the corresponding right, y1 and y2 and yn actually is on the line, right? It's on the line, right? It's on the line. So you can see this is the y1, big y1. This is the black dot is the actual demand, our actual sale, and the red dot is the sale that is on the trend line. All right. So if the one trend line exists that best fits it, what happens is that the difference, right? The differences between little y1 and big y1 should be smallest, right? Should be the smallest, and it should happen to all the dots. So all the data points here about this line from quarter 1 to from quarter 12. So in this case, we can actually come up with one equation, which is sum of squared arrows, right? Sum of squared arrows. So this is the arrow for the first point. This is the arrow for the second point, and this is the arrow to the for the last point. So add them all together. If we want to minimize. So this is because of more of an optimization method, right? We want to minimize this equation's data or result. So if we can find a line that can minimize this, means that is the best line, right? Means that is the best line. Okay, all right. Then how do we find out that? Because if this is we already know the little y's, right? These are the actual numbers. Then the y1 we can actually replace the big y1 with what? Remember this equation: y equals a plus bt, right? Y equals a plus bt So all we need to find out is what? Is the a and the b. If we know an a and a b, we can actually find the equation. All right. So y for each of the y's, y1 actually can be replaced by what? By a and b, right? By a and b, because t already know is 1. We already know t is 1. So we can be replaced by a and b. So this equation actually becomes becomes what? Becomes an equation with two variables a and b. Right? Because two variables a and b. So basically it's f, a, b. Becomes equation of two variables. And if you want to find the minimized number for this, we can actually do what? Do what? To find the derivatives, right? Find the derivatives of this equation and then let it to equal to 0. And then we can find out the relations between a and b. And then then we can find out what is the best trend line or the number for a and b. So this is how we come up with the equation to calculate use some of the squared arrows to find out the trend line. There are going to be a lot of equations, a lot of calculations and in it. But here I'm going to just give you the equation here. So the equation calculated here is b equals to sum of t times y, right, minus n times t average times y average divided by what? Divided by the sum of t squared. This is square first, and then sum it together. And then minus n times t average first, and then squared. So this is the equation for b. Now what about a? Because we already know the relationship between a and b, we can actually calculate easily with a. So a will be equal to what? A will be equal to y average minus b times t average. So this is how we calculate the a and b. Now we know the a and b data, we can find out the trend line. If you want to forecast, the period from 13 to forward, then we can just use change the t to be 13 to 16. So eventually the trend line we find out is that the A is 441.67 and B is 359.6. You can hear this is the A, this is the B, and then times 13, we get the forecast for period 13. Then times 14, get the forecast for 14. Times the 15 for a period 15, and then times 16, we get the forecast for period 16. So this is how we use a trend line to find out the forecast for the next periods, if you want to look at longer term of the predictions. All right, so doing those calculations manually will take a little bit more time. There's another way which is much easier, which is to use the Excel to do it. But first, if you want to Excel, there is a function that is not naturally in your interface. You will have to add in from Excel. So it's very simple. You just go to File, go to Options. There's Add in, and then choose Analysis Tool Pack, and then there's the Manage function. Right? In the Manage function, you click. There's a Go, select Analysis Tool Pack. So this is how you include that add-in function in Excel. So after that, you should be able to see a data analysis. You should be able to see a data analysis function in the data ribbon, right? And then so the interface you will see is actually this interface will pop up and ask you to choose what is the Y range, what is the X range, and also what is the output range. So here you can see how, of course, first of all, you need to include all the data in Excel, right? The quarters and the sales. All right. So next, after you come out with this result, what you're gonna show is this part. So this is the result. It will automatically generate it from this analysis tool, and you need to look at the two important factors. The one is this intercept. Another one is x variable, right? So the x variable is 359.6. So this is what? This is B, right? And intercept is A, which is 441. So you can see from these two numbers, you can find out what is the trend line. So this is how you use Excel to find out the trend line equation. All right. Next, I want to talk about time series decomposition. Because especially in a more complicated data or more complicated forecast, it's not only the trend itself. There are gonna be several different elements or factors included in it. For example, trend is one, and also maybe there's seasonality. Also, there are a lot of randomization, right? So, well, how do we find out that and decompose those in series so we can find out the actual values for these elements to generate our predictions, right? So this is a time series decomposition is a way how do we do that, and we learn about how do we generate the trend line. Now what about the seasonality and the randomness? So there are also cycles and autocorrelation. We're not gonna focus on that in this course, but most of the common factors will be the trend line, seasonality, and randomness. All right, first let's look at seasonality. So seasonal variations may be either additive or can be multiplied. So additive one will be more like the first graph A. You can see it's keep going up with the trend, right? There is a trend. There's seasonality, right? Seasonality. There's up and downs, and it's very regular, and also the multitude is kind of the same. Well, in the second graph, which is the seasonality can be multiplied. In this case, it's actually the trend. We use the trend times seasonality. Use the trend times seasonality. You can see how the multitude of seasonality actually changes, but also it is strictly applied to the time periods. So the first one will be the trend plus seasonality. The second one will be the trend times seasonality. All right, now let's look at one example. How do we determine seasonal factors? So seasonal factor is that the ratio of the amount sold during each season divided by the average of all seasons, right? So seasonal factor. Remember, it's a ratio, right? It's a amount sold during each season. So it's the actual sales of that season divided by the average of all the seasons. Right? For example, in this historical data, we can see that we have spring, summer, fall, winter, right? And we have their sales. 200, 350, 300, and 150. All right. In order for us to find out the seasonal factors, first we need to know that what is the average of all the seasons, right? So average of all the seasons will be added up all together divided by 4, so which is 250. Then we use 200 divided by 250, so we can get the seasonal factor here. This is a seasonal factor for spring, and the summer seasonal factor will be used 350 divided by 250. Now we get 1.4, right? Now you can tell actually the average, right? The average will be like a standard, right? It's more like a standard. So if it is smaller than 1, what happens? If the seasonal factor is smaller than 1, means the past sale, the sale is actually smaller than the standard or the average. Okay. So this is how we find out the seasonal factors. All right. Next, how do we generate forecasts for the next few periods? Well, first of all, we need to know what is the total forecast for the next year, right? Next whole year. The next whole year's forecast we generate is 1,100, right? Well, in this case, we need to find out what is the average, right? What is the average for each of the season? The average for each of the season we can get is 275. And then next is times, to let that number times the seasonal factor. Then we can find out the next season forecast. See, the calculation for determining seasonal factor and the find out the forecast is actually reversed. So in the determining the seasonal factor, we divide it by the average. Now the forecast, we have to multiply the seasonal factor back, right? Multiply the seasonal factor back. So this is because 275 is average. It's simply the average without any seasonality, right? And then we know the seasonality, then we times the seasonal factor to find out the forecast. So this is how we find out or determine seasonal forecasts. All right, now let's look at one example here. So use the data for periods 1 to 12 and then apply time series analysis and to forecast for periods 13 to 16. All right, we have all these quarters from quarter 1 to quarter 12, and then we have the demand from 600 to 4900. All right, so how do we do this? We have 12 periods, right? We have 12 periods, and also there's a seasonality, right? There's also a trend. Right? Also a trend. So in this case, we have a seasonality, we have the trend. How do we find out the forecast? Well, in order to determine the forecast, we need to know what are the seasonalities, right? What is the trend? But the question is, should we find out seasonality first, or should we find out the trend first, right? We see this line that is always like this, right? Now the question is, should we find out the trend line first, or should we find out this seasonality first, right? So usually in this case, when we are decomposing a forecast or decomposing a set of numbers, what we usually do is that we first gonna find out the seasonality, right? Because seasonality usually creates some of the noise when we are determining the trend line. So that's why we usually find out the seasonality first, right? All right, now let's look at this how to solve this question. And because the question is because we have 12 periods, right? When we are looking at seasonality, usually we look at spring, fall, spring, summer, fall, and winter. There are only 4 periods, but we have 3 years of data. How do we do that? 3 years of data. It means we have 3 springs, right? We have 3 springs. Well, in this case, the first thing we need to do is we need to find out the spring's average first, right? The spring average first. So the first spring is, or first quarter for the first year is 600, and then the first quarter for the second year is what? Is the 2400, and the first quarter for the third year is 3800. So this is how we first need to find out the average of the same quarter, right? Find out the average of the same quarter. And then next, what we're going to do is we find the average of the second quarter, find the average of the third quarter, and then find the average of the fourth quarter. Now we know there are the averages of the 4 quarters. Do we know how to find out the seasonal factor? Yes, right? So basically we use this number, right, divided by the total average, right? Divided by the total average. All right. The total average should be when we add all the actual demand from quarter 1 to quarter 12 together, which is 33,350, right? Then we can find out the, so sorry, this is the sum divided by 12. Then you can get what is that average, right? Then you can find out the seasonal factor for each one. So this is the seasonal factor for the 4 seasons. Next, we found, okay, this is seasonal factor for the first season for first year. What about second year and third year? It should be the same, right? That's why we call it seasonal factor. It should be the same. So that's why the seasonal factors for the year 2 and year 3 should be the same. All right, next, let's look at, all right, we already find out the seasonal factor, but how do we find out the trend line? How do we find out trend line? Because we have the seasonal factors, we can actually find out a series of data, right? A data series that is without seasonal factors, right? Without seasonality, right? Without seasonality. So basically, we use actual demand divided by the seasonality. So we can find out the deseasonalized demand. So this series, this deseasonalized set of data. I mean, this data is a set of data that without seasonality. Basically, we are getting out of the seasonality away so that we can get a clear, a better set of data to determine the trend line. All right, so we have this decentralized data. Can we find out the trend line? Yes, right? We can use the prior equation to find out the trend line. And then the trend line we can calculate that is a B equals to 342.2 and A equals to 554.9. Then we can find out the trend line is this. Next, what we're going to do is we're going to determine, okay, of course, this is the equation. This is how you calculate that trend line in Excel. Next, if you want to determine or generate forecast, right? Generate forecast for the period of 13 to 16. What do? We first generate the forecast from the trend line, right? From the regression, 13, 14, 15, 16, right? We generate the forecast from the regression. And then after that, we're going to times this seasonal factor, right? Because this set of data is a set of forecast without seasonality. We still need to put the seasonality back. So that's why we use this number times 0.82, 1.1, and 0.9397, and 1.12. This is the final numbers are for our forecast. It includes both the trend line and also seasonality. Okay? So basically, this is how we solve time series decomposition and how to generate a new set of data. All right. So lastly, we're gonna discuss a little bit about forecast error. We know that errors will happen, right? There's almost impossible you can actually, accurately get the real number of the sale because that's the future. No one can predict the future. So what we're gonna do is we're gonna use arrows to track how well we are performing in our forecast. Right? So usually there are two sources of arrows. One is biased arrows. The other one is random arrow. We want to have random arrow because random arrows means there's no certain factor actually gonna influencing your forecasting. It's all random. Right? It's all random. There's nothing we can do about it. It's allowed. Well, the bias arrow means there is certain kind of factor, right? Are affecting our forecasting, right? So that kind of factor either we do not know, or maybe there's a certain mistakes that happened that we had to find out. Once that factor comes into play in our forecasting, means there's a consistent error. There's a consistent error. For example, it's always going up, it's always going down, but the random error will be always up and down, up and down, up and down. we can use average to reduce the noise of random error. But if after we use average, we still find out there's the bias, which means there's a bias error. All right, so there are different indicators we can use to track the errors. For example, mean absolute deviation, mean absolute percent error, or tracking signals. These are the common error indicators in our to track our forecast. What I'm going to do is first let's look at all these equations. I'm going to use one example to demonstrate how to use those error indicators to track our forecast. So the main one is MAD means MAD means, remember what? It's the mean absolute deviation, right? MAPE is a mean absolute percent error. All right, first, mean absolute deviation is we use the actual demand or actual number minus the forecast, right? So this is the difference divided on time, and this is sum of those divided by n. For example, if it's only first period, we only use A1 minus F1 divided by 1. If the 2 periods, then we need to use A1 minus F1 plus A2 minus F2 divided by 2, right? We're going to accumulate all these numbers. Well, the MAPE when I use it scales the forecast error to the magnitude of demand. So means we use MAD, which we already calculated, divided by average demand, So this is how we use MAPE to track that. And the tracking signal indicates whether the forecast errors are accumulating over time. So it's a tracking signal. And the equation is the running sum of the forecast errors divided by average mean absolute deviation. So this equation might look a little bit complicated or a little confusing, but once I use the example, it's getting a lot clearer. All right. First, what we know is in this example is that we know the months 1, 2, 3, 4, 6. We know the demand forecast, which is 1,000. We also know the actual demand. Right, actual demand for the periods from 1 to 6. All right, first we want to find out the deviation. So deviation basically is to use actual minus forecast, right? Minus forecast. So we can get the first one is minus 50, second one is 70, and then we calculate all the rest of the numbers. The running sum of forecast errors. So running sum of forecast errors means we're going to add up all the errors. Well, the first one, add up all the errors, is minus 50, right? The second one will be what? Minus 50 plus 70 to get this 20. Right? Well, and the third running sum of forecast error will be what? The three of them added up together, right? Added up together. So we can get it's 120. Consequently, we can see 80 is forecast error for the first period will be the fourth period added up all together. So this is how we find running sum of forecast errors. All right, next is absolute value of deviation. So basically, this is very simple to understand. We know the deviation, and the absolute value of the deviation will be only the positive numbers or the absolute values of these deviations. Well, the next one is the sum of absolute deviation. So the sum of absolute deviation, so basically we should add up all the absolute deviation together. So the first period, the 50, second period, add them two together, and the third period, we're going to add them all three together, and the first period, keep going on, right? So this is sum of absolute deviation. And then mean absolute deviation will be what? Will be using the mean, right? The first one is 50, right? First one is 50. This is the absolute deviation for the first one. And then how many periods? 1 period divided by 1, right? And second one is mean average deviation. We first need to know sum of the absolute deviation. Sum of deviation for the second period will be 120 divided by 2, right? Divided by 3, divided by 4, divided by 5, divided by 6. So this is how we find out the mean absolute deviation, right? Mean absolute deviation. Well, the last indicator is a tracking signal. The tracking signal equals to running sum of the forecast error, which is this one divided by mean absolute deviation, right? So it's minus 50 divided by 50 equals to minus 1. And then use 20 divided by 60, right? Equals to 0.33. So this is how we find tracking signals. So from these indicators, actually we can we can either draw a graph or use those indicators to find out how much deviation we have made or errors we have made during our forecasting. Then we can keep adjusting our equations, our models in order to generate better forecasts. So basically, that's how we do forecast. This is the introduction course for forecasting. There are going to be a lot of complicated forecasting techniques that involved in manufacturing, prediction or sales prediction or forecasting. If you're interested, you can always look for more information on that. I'm also happy to discuss that with you as well. So, all right, some of the takeaways from this class is the components. You understand what are the components of forecasting? The seasonality, cycles, randomness, trend, and the different equations that are for some simple methods like moving average, weighted moving average, exponential smoothing. Also the linear regression analysis to find the trend line. Then a little bit more complicated calculation will be how do we decompose a series of data and then to generate forecast with both trend line and seasonality. Lastly, when we'll talk about forecasting arrows, how to use forecasting arrow to track the performance of forecasting.